All right, now we are moving on to Euclidean geometry. Okay, so everything that you've learned with regards to Euclidean geometry in previous grades, it holds. It's going to help you. Nothing should have been forgotten by now. So we're going to do a new concept that is of circle geometry. But before we start with circle geometry, we're going to go through some terminology. Okay, so this round thing, we refer to it as a circle, and it consists of different sections. All right, so this area that we use to draw up a circle, the outside of a circle, that line there, the round line outside, we refer to it as a circumference. Okay, that is a circumference. So let's say that this point here of the circumference was point C, and this point of the circumference was point D. So if you draw a line from one end of the circumference to the other end of the circumference, we refer to that line as a chord. Okay, and notice that this chord will then give us a part of a circle. So that part of a circle, we then call it a segment. This bigger part will also be called a segment, but a bigger segment. All right. And then we also notice that a piece of a circumference is only referred to as an arc. Okay. And then we have the center of a circle. So any line that is drawn from the center of the circumference to the circumference, we call it a radius. Notice that there's also a line from the center to the circumference, that's also a radius. There's another line from the center to the circumference, that's also a radius. So we are having 3 radii there. So if it's one line from the center to the circumference, it's called a radius. If it's more than one, then the plural is referred to as a radii. And what we should know about the radii of the circle, just remember radii means more than one circle. The radius. The radii of the circle are all equal. So that means this line is equals to this line, which is also equals to this line. We need that knowledge a lot. Any line from the center to the circumference is a radius, and then more than one radius, we refer to it as a radii, and all radii of the circle are equal. And then another thing that we have to know is that when there's a line that is outside a circle but touching the circumference just once, then we refer to that line as a tangent. So that knowledge we're also going to need a lot. All right, so there are 9 theorems of circles that you have to know. You have to understand them. You have to know how to apply them. They are very, very important. 7 of these theorems you have to know how to prove. So that means they have to be in your heart. So in exam question papers, they will ask you to prove about 2, and then that will contribute about 10 to 12 marks. So it's not something to play with. So it's 9 theorems in total. You have to know how to prove 7, but all 9 you have to know, understand, and be able to apply. So theorem 1 of circle geometry states that if a line is drawn from the center of the circumference, from the center of a circle perpendicular to a chord, then it bisects the chord. So remember the word bisects, it means cutting into 2 equal parts. Bisect means cutting into 2 equal parts. All right, so you will see in this circle here, we have a line, we have a chord AB, then there's a line OP. This line is from the center and then it's to the chord. So we are told, you'll see that there's a 90-degree there. So that means we are told that OP is perpendicular to AB. That is given. We are given that OP is perpendicular to AB because they make an angle of 90 degrees. So that means what we are then to required to prove is that then AP will be equals to PB. That's the first theorem. Any line that's from the center and then it's perpendicular to a chord will cut the chord into two equal parts. All right, let's prove that. So with the proofs of the circle geometry, you always start with a construct. Okay, you will redraw the circle, what is given to you as it is, and then there's always something to construct. So in our case, what are we going to construct? We're going to construct line OA as well as line OB. Okay, so it's in a dotted line rather than a solid line because that is what we constructed. Let me repeat that. I used dotted lines, not a solid line, because that's what indicates that is what we constructed, not what we originally found there. You see that what they drew is a solid line, but what we construct, we indicate with a dotted line. So the marker will always know that that's what you added when they look at your structure. Okay, so we just added. We just constructed OA as well as OB. So then our focus is going to be on two triangles. That is triangle OPA as well as triangle OPB. All right. Okay, so let's have a look at that. So we said we are constructing line OA and line OB. And this has created two triangles. So we're going to say in triangle OPA and triangle OPB, okay, what we're going to try to prove with those two triangles that they are congruent. Okay, so how would you go about that? So this is something you've learned in the previous grades, and congruency was a lot used in grade 10. All right, so we're going to notice that by constructing that OA and OB, we were creating the radii, because both lines OA and OB are from the center to the circumference. And then what do we know about the radii of the circle? We know that they are equal. All right, so we will say OA is equals to line OB. So you always give your reasons with Euclidean geometry, the circle geometry. Always give a reason of your statement. Without a reason, your statement is false. So our reason in this case is that these are the radii. It's well known that radii of the circles are equal. So it's good enough to just mention that you're saying that they are equal because they are the radii of the circle. Another thing that we have there is that both triangles share side OP. Okay, so we're going to say side OP from triangle OPA is equals to side OP from triangle OPB. That is simply because they are common. It's a common side. They share that side. So that is our reason, which is good enough. Common. Okay, and then what else do we notice? We also notice that angle. Okay, let me just draw a line here so that we can go there. Angle OPA, this angle OPA, this angle here is equals to angle OPB. they are both equals to 90 degrees. Okay, so this angle is equals to this angle. They are both equals to 90 degrees. And what is the reason why we say that? That is given, we are told. Okay, we were told that they are perpendicular. So this is given. All right, so we were told that OP is perpendicular to AB. We know the things that are perpendicular, they create an angle of 90 degrees. Hence, we are saying that's given. So notice that we found two sides that are equal and two angles that are equal. And then we know from grade 10 that in a right angle triangle, if you can prove the hypotenuse side with another side, the right side, that are equal, then the two triangles are congruent. So we can then conclude that therefore triangle OPA is congruent to triangle OPB. What would be our reason from grade 10 in that case? It's just, we just abbreviated R, H, S. You don't have to write the entire statement. It is well known that RHS stands for right angle hypotenuse side. So that means we had two right angle triangles. And then we had hypotenuse sides of the two triangles and a right side being equivalent, making those two triangles equivalent. Since we have these two triangles equivalent, that means the remaining sides are then equal. Therefore, AP is equals to PB. You have to know this theorem by heart. I've seen it in a lot of question papers. Okay, so you will be given this circle, you redraw the circle, you construct, and then you prove the congruency. All right, so the next theorem states that a perpendicular bisector of a chord passes through the center of a circle. If you notice, that is the opposite of theorem 1, because that one had said a line passing through the center perpendicular to the chord that it bisects. So now we are told that a perpendicular bisector must pass through the circle. That's what we have to prove. What are we given? You are given what we were supposed to prove in theorem 1. Now you are given that AP is equals to PB. Remember theorem 1, we had to prove that. Okay, now it's given. And then we are also told that CP, line CP, is perpendicular to AB. Okay, so that means we need to prove then that this PC, line PC, is passing through the center of a circle. How do we go about that? So what we're going to do on line CP, you're going to create a point, any point. On line CP, you're going to create a point and name it anything. All right. So you will see that point O was created there. Okay. And then since now you created point O, you have to construct also. You always have to redraw. What we're going to construct, just in theorem 1, we are going to construct OA as well as OB. We are constructing the construction. We are join OA and OB. OB, creating two triangles. So we're going to approach this the same way we did in proving theorem 1. All right. So now we have two triangles. In triangle OPA and triangle OPB, okay, what are we getting in those two triangles? Let me just fix this here. in, okay, so in triangle OPA and OPB, the first thing we notice is that AP is equals to PB. AP, line AP is equals to PB. That is given. That's our reason. You always write a reason. Remember, you don't leave a statement like that. If it's given, you say given. So this is given. They told us that AP is equals to PB. Okay, it's either on the statement you will get this, or you can also notice by those two sticks there that those two sides are equal. And then we have side OP there. Those two triangles share side OP. So we will say OP is equals to OP. That is a common side. All right. And then we also again know that OPB angle OPB is equals to angle OPA. Please notice that I put a head on in the letter that's in the middle to indicate that it's an angle OPA. So that is OPB, this angle here, and OPA, this angle here. They are both equals to 90 degrees. This is given. We were told that CP is perpendicular to AB. So that is given. Okay, so we just proved two sides and an angle of two triangles that are equivalent. What does that mean? It then means that triangle OPB is congruent to triangle OPA. It means that triangle OPB is then congruent to OPA. So that means the remainder of the sides are then equal. Therefore, OA is equals to OB. Okay. And what is the reason here? Forgot the reason. We never leave a reason as it is. So we just proved side angle. So we just proved that two sides and an angle of two triangles are equivalent. So that's one of the conditions of congruency. So that means triangle OPA is congruent to triangle OPB. Then the remaining sides are then equal. But then we also remember that that can only mean that OA and OB are a D, because it's two lines that are equal from some point. What does then that mean? It will mean that any point on CP, it wouldn't matter whether we put it there or there or there, would have been a center. That means O is a center of the circle. Okay, just notice it's two lines that we proved to be equal and they're from some point. And then we have a knowledge that if we have two lines that are equal in a circle, then they must be from a center. They should be the radii. Okay, that's what we just proved, that O then should be a center of that circle.